In the last week, we introduced the concept of chaos via the definition of a horseshoe. In this video, I want to make an important remark about a gap that appeared in the notes, problem set solutions, and exam solutions over the last few years. First, to remind you, the definition of a horseshoe was as follows. A map F has a horseshoe if there exists a closed interval J in I and subintervals I0 and I1 in J such that both of f of I0 and f of I1 is equal to J. Most importantly, we indicated that if a map has a horseshoe, then it must have a transition graph that contains the subgraph shown in the image. A map was defined as chaotic if it contains a horseshoe in f to the n for some n greater than or equal to 1. However, what you'll notice in the notes is that throughout, we use the subgraph consequence as a condition of sufficiency for a horseshoe. Specifically, in some problems, when we could detect that such a structure exists, then we claimed that this was a horseshoe. For example, in chapters 10 to 12, question 1, we have this statement. And similarly, in the 2015-16 exam, question 3, we have this statement about the induced subgraph of the f-squared map. Because of these inconsistencies, I'll strengthen the statement in chapter 12 so that it does indeed provide sufficiency, and you're free to use this in the problem sets and exams. I'd be interested if you can prove that it's indeed sufficient, and I believe that in simple cases, it can be done. I'll give an example in a minute. Before going further, I want to mention that the definition of a horseshoe that you see in the notes can be found in the official reference, which is Paul Glendining's book, Stability, Instability, and Chaos. The definition is in chapter 11. I want to end this video with a point of interest, which is to show you how to prove the important theorem from our course that period 3 implies chaos, using this official definition of a horseshoe. Okay, so remember, the idea is that you have a 3 cycle in F, so x0 is sent to x1, which is sent to x2. Let's now show that this is enough for a horseshoe in f squared according to the original definition of a horseshoe. We'll do this fast, so you'll probably need to pause the video. The trick is to find these special points in y and z. Z will be a fixed point in the map, and y will be in the pre-image of z. First, the existence of z between points x1 and x2 is as follows. Define the function g, which is equal to f minus x. Notice that g on x1 is greater than 0, while g on x2 is less than 0. By the intermediate value theorem, you must travel through 0, and hence there exists such a z. Next, the existence of a y between points x0 and x1 is done in the same way, but you define your g to be f minus z. Again, by the intermediate value theorem, there exists a point where g is equal to 0. Okay, so now you let j be the interval y to z. We know 3 things at this point about the f squared map. First, f squared sends z to z. Second, f squared sends y to z. And third, f squared sends x1 to x0, which is less than y. Draw the graph of f squared. This is shown in red. When you're at y, the graph is at z. It dips to a point less than y and then increases again to z at the end. By the graph, you can see that there has to be at least 2 intersections by the intermediate value theorem again. In particular, there has to be a smallest r in y to x1 such that f squared sends r to y, and there has to be a largest s in x1 to z such that f squared sends s to y. Set I0 to be y to r and I1 to be s to z. Check that f squared sends I0 to j and sends I1 to j, so f squared has a horseshoe. This proof, by the way, gives you an idea of how you would prove sufficiency of our remark from earlier. Basically, you want to take the original I0 and I1 intervals, which form the subgraph structure, and develop smaller intervals which have a similar property to the ones that we used in the proof here.